Okay, so good morning everybody. My name is Andrew Butte. I'm the Group 1 reporter for the Rankine cycle experiment we conducted last week. So some background behind Rankine cycles is they're used for power production. They're the most widely used cycles for generating power, especially with coal and nuclear systems. The process for power generation is relatively simple, with water being turned into steam, that steam being used to turn a turbine, and that turbine in turn creating power. So there's 5 main steps to the Rankine cycle. So you have water being pumped into the boiler as shown in the diagram on the right here, and then that boiler heats the water, producing steam at a high pressure. That steam is released via a nozzle from the turbine, which causes the turbine to rotate. And as the turbine rotates, it turns a generator, creating electricity. And finally, that steam is cooled down and condensed back to liquid water. So Rankine cycles are particularly attractive because the working fluid is recycled versus a Brayton cycle or a jet engine cycle where it's burned off. So the theory that was pertaining to our experiment included these equations. So in an ideal cycle, the difference in heat in and heat out and the minus the work difference between the turbine and pump would sum to 0. The equations shown here on the left correspond to the numbers on the diagram shown here on the right. So importantly for our case will be the turbine work, which is the enthalpy at state 3 minus the enthalpy at state 4. The boiler follows a similar set of conditions at H3 minus H2, the condenser H4 minus H1, and the thermal efficiency equation is also shown here. So the equipment that was used was the Turbine Technologies Rankine cycler. The key components were the turbine, which you can see over here is very small, the condenser tower itself, the boiler and the boiler fuel source, which in this case was a propane fuel tank. Note there's no pump associated with this Rankine cycle, and the boiler is gravity fed. The procedure was water was added to the boiler at 4,600 milliliters. This is a change from the 5,000 milliliters reported in the lab manual, which changed due to ASTM standards changing. The propane tank's initial weight was measured, and then the propane tank was connected to the boiler. The boiler was allowed to heat up, and the pressure of steam inside was built up, and once the steam emission valve was open, the system was allowed to stabilize operating conditions, at which point data was recorded, the burner was shut off, the system was shut down and steam was allowed to fully cool or be released from the system, and then the final amount of water in the system was recorded, and the final weight of the propane tank was also recorded. So the raw data was collected via a PDAC system in the lab. The quantities recorded including the boiler temperature and pressure, the turbine inlet and exit conditions, the fuel flow, and the voltage, current, and power produced over the cycle. Shown here on the right is table 1, which shows all the data for the steady state point I chose to analyze the system at, which is at t equals 250 seconds, and I'll get to that in a moment. So the key steady state indication plots I have shown here, the others are in the appendix. If there's any questions, I can answer them after the presentation. So shown here are the boiler temperature and boiler pressure. Note the boiler pressure never fully stabilizes, however it does stay relatively consistent within a range of about 25 kPa. However, in an ideal system, you would want that to fully stabilize, which is what you would use a pump for typically. And shown here are the turbine temperature and turbine pressure plots versus time. Note the turbine outlet pressure is much lower than the turbine inlet pressure. And the steady state point for analysis, like I said, was selected to be time equals 250 seconds because it fell within the steady state window for all plots. And shown here on the left are all data values recorded for that instance in time. And shown on the right are the properties calculated for those different states based off those temperature properties from the steam tables, saturated liquid and vapor tables, compressed liquid tables, and superheated vapor tables. Also, the mass flow rate was calculated based off the volume of water used in the cycle, as well as the specific volume and the time of the turbine. So the results, the turbine work ended up being around 35 kilojoules per kilogram. The heat rejected from the condenser, as we would expect, was much larger at just over 2,400 kilojoules per kilogram. The heat added during the boiler stage was similarly over 2,400 kilojoules per kilogram. The thermal efficiency was found to be very low for the cycle at 1.387%. However, this can be due to some inaccuracies and inefficiencies in the cycle itself, which I will discuss in a minute. And the generator efficiency was also calculated based off the power from the generator over the power reported from the turbine at the steady state instance. So as I mentioned, there's some uncertainties in the system. They don't necessarily come too much from the actual apparatus itself, as data was recorded using the digital PDAC system, which has a very high resolution, meaning the resolution error was fairly low. However, as I mentioned before, the boiler pressure never reached steady state because there's no pump. So therefore, improper assumptions could be made when it comes to defining the different state variables for enthalpies at the boiler conditions. So as I mentioned, discussion-wise, there's some improvements that could be made in the system. Obviously, it's a very small system, and therefore having a pump isn't fully necessary. However, because the boiler is gravity-fed and their boiler pressure never fully stabilized, it leads to some problems with assumptions that are made for a typical Rankine cycle. Also, the generator efficiency was very low. However, this could also be due because we are braking the turbine to basically stop it from rotating fast to preserve the system. Also noted the thermal efficiency was low. However, this could be improved if the turbine exit conditions were a saturated vapor rather than a superheated vapor. However, there are causes and concerns why you don't want that to happen. For example, if it's a liquid vapor mixture, you can have steam condensing on the turbine blades, which can damage them, causing images such as this. Any questions?